Okay, so let's consider this example. Okay, now we have three particles, Q1, Q2, and Q3, which is this one, and this one. So a Q1 is plus 2Q, Q2 is negative 2Q, and Q3 is negative 4Q. So they have distance d from the origin, d here, and the net electric field is produced at the origin. What is the net? Actually, it asks you to calculate the net electric field produced at the origin. At the origin. So so actually, we need to calculate E1, E2, and E3 generated by Q1, Q2, and Q3, and then we add them together. Then it's done. So, so technically, it's not difficult. So E1 is just K times Q1 is plus 2Q, and then D square. And then actually R1 should be this direction. R1 should be this direction. R1. And then for E2, we have K. The charge Q2 is negative 2Q over D square. And actually R2 is in the opposite direction. Which means it is actually minus R1 hat. Right? R1, R2 hat has the opposite direction with the same length. So R2 hat is minus R1 hat. So we have two negative sign, and then we can merge them together so that we have K 2Q over D square times R1 hat. So actually, they are the same. So for E3, it is K times minus 4Q over D squared. And then R3 is in this direction. Maybe we can just assume. R3 is in this direction. Okay. So that we can have a minus R3 hat like this. So it's just to make K 4Q over D square R3. And actually, you can just make R3 hat onto the bottom left. So actually, we know that E1 and U2 are the same. So we know that E1 plus E2 is nothing but K times 4Q over D square R1 hat. And we should be able to know that E should be E1 plus E2 plus E3, which means that it should be 2E3 cosine 30 degree and point to the I direction, because E1 and E2, when we add them together, it is this one, and E3 points to is this one. Both of them have 30 degree with the x-axis, and actually the magnitude are the same. The magnitude of them are the same, so that we have the x component. X component is E3, the magnitude of E3 multiplied by 30 cosine 30 degree. So we have two. For the y-axis component, they cancel each other, so that all of them point to the positive x-axis. So something like this. And then you just substitute all the numbers, the final answer is 6.93 over 4 point epsilon 0 times q over d squared I hat. Well, you may ask, why don't we just substitute 8.99 times 10 to 9 into it? Actually, you can do that, but this is somehow more beautiful in some sense. So up till now, any questions? If you really have question, you try to ask, and you try to slow me down. Otherwise, I may talk faster and faster. So the next one is called the electric field due to a dipole. So now we define what is a electric dipole. So actually, the mathematical definition is P vector equals to Q times the D vector, distance vector. Actually, what is it form the electric dipole? The electric dipole consists of two charged particles. Actually, two particles with charge of equal magnitude Q, but opposite sign, which means that this one has positive Q charge and another one has negative Q charge. They should have the same amount but opposite sign. And they separate by a small distance d, and they keep this distance. So we call it dipole. In Chinese, we call it 偶极，偶就是两个嘛，或者双数，偶极就是两个极啊，偶极 dipole。So you may ask why don't they attract each other and then they become electrically neutral? So this is a very interesting question. We'll model a dipole like this. We have two opposite sign charge, but they will remain the small distance. Actually, in the real world, we will have this kind of stuff. You can just imagine the Earth and the Moon will have gravitational force, but they should attract each other, but the Moon will not collapse Earth in the forthcoming future. As you know that the Moon has some sort of velocity, which means the kinetic energy. So suppose we have the Earth, then the Moon. They should go somehow like this. So it will keep the kinetic energy, and then you have circular movement, so that the Moon don't actually crack on the Earth, somehow like this. Or you can imagine you have a H2O H plus, you have H plus, the hydrogen ion, and then you have O2 minus. Then they will somehow like this with the hydrogen bond, right, if I remember correctly, but they will not try to collapse to something unknown. They will just keep this distance, and then they will try to rotate something like that. So here we have electric dipole. So now we will define the electric dipole is somehow is a vector. It's a vector. So so first thing first, we have the SI unit. SI unit is coulomb meter because Q is charge, so the SI unit is coulomb. D is the distance, so the SI unit is meter. So the SI unit for the dipole is coulomb meter, nothing special. And it is actually a vector, so we not only need to consider the magnitude, but also the direction. This is a difficult part for a vector. So here, Q is for sure a scalar, which doesn't have a direction. But we can actually define D as a vector. The distance can be a vector, which means that if we define the distance from the negative charge to the positive charge to be the vector, actually the position for the negative charge to the position of the positive charge, and then we connect them, and this direction is the distance vector. So distance can be a vector. And in the next chapter, you'll know that area can also be a vector. Area can also be a vector. But now you only consider the distance is a vector, so that the electric dipole has a distance like this. For this one is pointing upward. This is the direction of the electric dipole. And actually, for this case, suppose we place the electric dipole here. And we consider the electric field on this x-axis. And suppose the distance from the point you concerned, you imagine the axis has a 0 point here, We have a c-axis, has a 0 point here, and then pointing to upper direction. This is the z-axis, and then the point here has a distance from the original point is z. So the electric field at this point is something like this. So which is 1 over 4 pi epsilon 0 2 q b over z cube. Or why there's a cube, not z square, is z cube. Actually, there is 2 here and 4 here. Maybe you can just cancel one of the 2 so that it becomes 1 over 2 pi epsilon 0 is okay, but sometimes to make it like this is better for you, because sometimes when you are in the exam, you try to plug in the values. You try to plug in 8.99 times 10 to 9. And if you just cancel, you forget the factor of 2. But here you will still remember it. I can see this term 1 over 4 pi epsilon naught, which is 8.99 times 10 to 9. Then you will still remember there's a 2 here. There's some chance that you can escape this kind of mistake. So for the next slides, I try to tell you why there is a cube here. It's a cube here. It is not so difficult because it is some algebraic calculation only. So here, when we try to calculate the electric field at point P, and we know we have two charges, then we can calculate the calculated E field generated by plus Q and negative Q one by one, and then we add them together. And we know that this one is plus Q, so it generates a positive E, and then this one generates a negative E. So we make it a magnitude so that we subtract them. So it's somehow like two similar value, and then you cancel both of it, so it remains a one order lower. That's why it will have C cube here. So actually, we can just use the equation we have just now. We have E equals to K times Q R plus square. R plus is this one. Z plus half of D. And R minus is this one. This one is Z minus half of D. This one is Z plus half of D. So the only difference is this term. So KQ can be factored out. Then we have 1 over R plus square, which is Z minus D over 2 square. And we have R minus square, which is Z plus D over 2 square. So nothing special. And then we can just factor C square out. So we have C square here. And then this is square, so that we define Z for both term. So we have 1 minus D over 2Z, because we have D over 2 here, so we divide by Z, so it becomes D over 2Z. And this one is 1 plus D over 2Z. So some algebraic calculation, and then you can just try to multiply the common factor of them, and then you add them together. So you know that this one is square, so that you use the a plus b square is a square plus 2ab plus b square. You use this formula so that you know that the numerator will become 2d over z, because actually we have 1 plus d over 2z, so we have 1 plus d over z plus d square over 4z square, and minus 1 minus d over z plus d square over 4z square. So this one cancel with this one. This one cancel with this one. So we have this one minus this one. So we have 2d over z here. And then this one is like this. So finally, we assume that z is much larger than d. Which makes sense because for a dipole, d is usually very, very small, and then we concern upon much far away. So that now we assume z is much larger than d, which means that this term is tends to 0. This term tends to 0, so as this term, so that these two terms will tend to 1. So you can just ignore this one. Then you have 2d over z over c squared. So finally you get k2qd over c cubed. And actually, in the previous one, we define P to be QD. So we can write QD to be P. So the formula at 22.9 is derived like this. Any questions? No question， 好簡單。So next one is the electric field due to a line charge. Actually, we'll use calculus here, but well, last year's a student commented, or it's just you just integrate a constant over a circle, and it's feel like you use the calculus, which is not so necessary. But actually, this is a starting point. I don't actually always provide the most shortest solution here, because some of you may get lost. This is a step to let you know how to go to more complicated case. For a constant case, if you still use it, you will get used to how to use the calculus to solve this kind of problem. Then for a more complicated example or problems, then you may be easier to follow. The point is somehow like this. So here, so we have a line of charge. So you consider this is a circular ring, which has a positive charge here, So it is somehow. So you can consider it in a 3D space. You have a circular ring. Somehow like this, and then it should have a center, right? So another axis is perpendicular to it, and then this is what we call the z-axis, and then we consider the electric field on the z-axis. Actually, you may ask, how about the electric field at here? But it is difficult to get a close from. So it only tells you how to calculate the E view on the x-axis. Okay, so here, so the equation for E field set up by a particle does not apply to the extended object with charge, which means that just now we know that the equation E equals K times Q over R squared is suitable for point charge. If you have multiple point charge, you can still use it and then you add them together. But now this is not point charge anymore. There is a ring, and then some of the charge Q or whatever, maybe Q, which is equally distributed on this ring. So you cannot tell this is a point charge. But because if it is really a point charge, then you integrate them, then it will be infinite charge there. So actually, you need to consider a infinitesimal small length ds. There will be some charge on it. Then you calculate the E field generated by this segment. So it would be like this. And then you calculate the E field generated by this one, and then you add all of them together. So you know that it is a integration. integration. You try to divide it, and then you add them together. So it is integration. Yeah, so is charge Q. Yeah, so the point here is that you can imagine here you have ds here, so that it will generate the dE correspond to this ds, so which will have an angle theta with the z axis, the z axis. So now you can imagine we have ds, because it is a perfect circle. We have a perfect circle, so we have dE like this, and then you can imagine on the circle you will have symmetric part, which is here. Maybe I use a red color. You can see. Okay. Here. So we have maybe ds prime, which is symmetric to the ds, which is symmetric to the ds. So it will generate the dE in this direction. Right. Right. So you can see if you just cut it down, it will be the circle, the figure like this, for this ds is generate dE here, For the ds prime, it generate dE in here. Because for a perfect circle, you can always find ds is symmetric to ds prime, so that all the vectors are on the same plane. For the other ds, for the ds here, you can find, for ds1 here, you can find ds1 prime symmetric to it. For this one, ds2, you can also find ds2 prime, which is symmetric to it, with respect to the origin point. So in this case, dE are on the same plane, and then for the horizontal component, they will cancel with each other. So that's, we don't really need to calculate the horizontal component. And the only component is the vertical component, which is actually dE cosine theta multiplied by 2, because we have two of them. They will add together. So now we have a right angle triangle. This side is z, this one is r, and the radius of the ring is capital R. It's a capital R. So that when you learn the trigonometry in high school, you should be able to know that cosine theta is z over r. The adjacent sine over r. So r is square root of z squared plus capital R squared, according to the Pythagorean theorem. 毕氏定理，或者你叫勾股定理。So R is square root of z squared plus R squared. Because R is not a known value. The only known value is z and capital R. So that we try to eliminate small r, and then we try to express it as z squared plus r squared and take the square root. So square root, we can write it like this: c squared plus r squared to the 1/2 order, 1/2 power. So now, just now we have dE cosine theta, dE cosine theta. So you can just substitute cosine theta into here. And what is dE? dE is nothing but lambda ds over r squared. Why it will like this? Actually, we define a linear charge density lambda here, which is the 电荷密度线电荷密度线性的电荷密度。So we know that the total charge is Q, and the radius of the ring is R. So that the length of the ring is 2 pi R. 2 pi R. So lambda is nothing but Q over 2 pi R. So actually the charge on ds is the density times the length. ds is the infinitesimal small length. So this is actually the charge on this segment. So this is actually the Q, not small q. Small q should be used here. Maybe you can use big Q, whatever you like. But after we cut it into many small segments, we can regard this one is a point charge. But actually, we need to know how many charge on this infinite small segment. And then the R between ds and t is small r. And we also know that r squared is z squared plus r squared. And then we multiply it by this one so that it becomes c squared plus r squared to the 1.5 power. And here we just rearrange the term lambda z. So we have z lambda here, ds we put it at the back. So now we know that ds, the charge on ds will generate dE cosine theta like this, and it can be expressed like this. So we already know one part of it, and then we know the expression. Then what we need to do is just to integrate over the ds. We integrate over the ds, then we will know the final answer. So ds is somehow like this. So we know that the total length is 2 pi r. So we integrate from 0 to 2 pi r over ds, then we'll get the answer. And as you know, this is a constant to s. So integrating this is very trivial. So this is a constant. So we integrate this. So we have this one multiplied by 2 pi r minus 0, which is 2 pi r. Then we can have lambda equals to q over 2 pi r, which means that q equals to 2 pi r lambda. So this 2 pi r lambda becomes q. Actually, this one should be small q. This one should be small q rather than capital Q. So the green term becomes small q, like this. So the final answer is like this. Which means that if you know the radius of the ring, and you want to know the electric field here, which has a distance z from the origin, from the center of the ring, then you can substitute QZR into this equation. Then you can find the E at this point. E at this point. So now if we imagine Z is much larger than R, just imagine you calculate a point very far away from this ring, which means Z is much larger than the radius of it. Z is much larger than the radius of it, then Z is much larger than R, which means that Z squared plus R squared is Z squared, because this one is much larger. So you can ignore this term. So Z squared to the 1.5 power will become C cubed, and one of the order cancel with this Z. So we have something like this. So it is something like you have a circular ring, and then you consider a point which has a distance z with it, then it will be E equals to 1 over 4 pi epsilon 0 Q, this is Q, equally distributed on this ring over Z squared. And now you imagine, for another case, you also want to consider the E field at this point, but now we have a point charge here, which is Q. They also have a distance Z. So the E field generated at this point is actually the same. It's actually the same. It is something similar to the shell theorem I mentioned yesterday. If this distance is much far away, then this circle is just like a point. It's just like a point. You can interpret this equation like this. So up till now, any questions? So we have a sample problem. So we have a plastic rod having a uniform distributed charge, negative Q on this rod. The rod has been bent in 120 degree, circular arc of radius R. The radius is R, and then this angle is 120 degree. So the charge is negative Q. So in terms of Q and R, what is the electric field E to the rod at point P, which is the center of this arc? Center of this arc. So just now we calculate the electric field for the whole circle at the z-axis. Now the ring is not complete; it's just a partial arc, and then we try to calculate the E view at the center of the arc. So now you can imagine if you place it here, which means that you have 60 degree on the upper plane and another 60 degree at the lower plane. So you can always find ds, which is symmetric to the ds prime on with respect to the x-axis. So it's just a mirror image, 镜像的对称. So actually this is negative charge. So you know that for this ds, it will have dE pointing to this direction, the upper right direction. For ds prime, it will point to the bottom right. So you just decompose it. So the y component will cancel with each other, and the x-axis component will superimpose. So they add together. So according to this argument, we only need to calculate the dEx, which is actually cosine theta times dE. So we know that dE is actually k times lambda ds over r squared, which is the radius of the circle, or the radius of the arc. And dEx should be dE times cosine theta. Which is k times lambda ds over r squared cosine theta. So ds is r d theta. I suppose you should know it in high school, which means that the length of the arc is the radius times the angle. Somehow like this. This is d theta, and this one is r. So this one ds is r times d theta. So dEx is k lambda r d theta over r squared cosine theta. So one of it can be cancelled. And yeah, so one of it can be cancelled, and then we place it here. So the total E should be we integrate over dx over L, which is nothing but minus 60 degree to 60 degree, which is minus pi over 3 to pi over 3. And then we just plug all of them together. K times lambda cosine theta over r squared d theta. I only reorder cosine theta in the front, so I just plug this term here, which is nothing but dEx. So we can have lambda over 4 pi epsilon 0 r. K is 1 over 4 pi epsilon 0. So we integrate cosine theta, which is sine theta, and then we substitute pi over 3 and minus pi over 3, and then we subtract them. So the final answer will be square root of 3 over 4 pi epsilon 0 r lambda. And then we also know that Q should be lambda times 2 pi over 3, which is 120 degrees. So we should be able to know that lambda is 3Q over 2 pi r, 2 pi r, which is the length. So finally, we can write that E is 0.83 Q over 4 pi epsilon 0 r squared. We only need to substitute lambda into here.